morning, everyone. Today we are going to discuss a very important topic which to some extent has an important role in shaping the present day surface of the earth. So that is weathering of the rocks. Weathering is the process of disintegration and decomposition of a rock at or near the earth's surface. We know that the rocks, maybe the sedimentary, metamorphic or the igneous, they form at deep down the earth. The plutonic igneous rocks, they form at the deepest level. Then the metamorphic rocks also, they form under, because of the action of high temperature pressure, they also form at deeper level. And the sedimentary rocks form near the surface. Now these rocks, they, due to the forces, they come up on the surface and are exposed on the surface of earth. So this process of weathering is a slow and subtle process. However, it is basic part of the rock cycle. We'll be discussing rock cycle, and it is defined as the irreversible structural or mineralogical breakdown of rock through the cumulative effects of chemical, physical, biological processes operating at or near the surface of earth. Now you can look at the rock cycle that I briefly discussed just now. So originally you have got the magma which cools down and forms igneous rocks. This magma in the volcanic igneous rocks, it comes out on the surface in the form of lava, and there the rocks are formed. So these igneous rocks, they come on the surface, they get weathered, they get decomposed, and this process of weathering, then you have the formation of it is decomposed and fragmented and transformed into sediments. These sediments, then they are deposited under different conditions and they form sedimentary rocks. These sedimentary rocks, they undergo metamorphism because of higher pressure and temperature conditions, and then these metamorphic rocks, if they are subjected to even higher pressure temperature, they again melt and form the magma. Now these sedimentary as well as metamorphic rocks, they can be uplifted and exposed on the surface, which undergo this process of weathering. So this is the rock cycle that is observed. Now here I am trying to show you a sculpture of an elephant made out of rock. Now you can see that this is a freshly made sculpture where the surface is very, very even. There is no roughness on the surface, whereas if you look at these idols, which are relatively older ones, some 5, 6, 7 and 100 years or 1000 years old, now because of the atmospheric conditions, they have been subjected to removal of the material, the disintegration of the rock on the surface, and hence you can see that they are not as intact as was the earlier one. You can have it is pitted, so some of the portions, they have been removed. So we say that these have been subjected to the process of weathering. Just to explain how this happens, I have taken examples of clothes, paintings and buildings. We know that originally this was a new cloth. Now when it is subjected to mechanical and the chemical processes, gradually it decomposes, it disintegrates, and so similarly you can see the painting. Once it must have been a complete painting, and here you can see that the colors, they have been coming out, it has become dull, and still you can see at some places the original texture, the original design. Similarly, you have a building which must have been constructed few hundred years ago, or tens of years before. Now this, because of the atmospheric conditions, because of the we can say the not good keeping of this building, it has disintegrated. So just like these objects, they have got disintegrated with time, the rocks also undergo physical and chemical changes that are natural, and they undergo the process of weathering. So here this is a diagram that shows how the rocks they crystallize out of the fractional crystallization of magma, where you will be learning in due course that there are two series. One is known as the discontinuous series, and this is the continuous series. Here we have got the minerals like olivine, which is magnesium iron silicate. Then we have got the pyroxenes, which are calcium aluminum iron silicates. Then amphiboles, group of minerals which are double chain ionosilicate minerals. So these, the original magma, originally olivine would form, then whatever remains out of that, the pyroxenes will form, then the amphiboles, then biotite magma, and at the end the quartz will form. Similarly, out of this plagioclase series, which is originally it is calcium rich minerals will form gradually as and when the segregation takes place, and then in the end you have the sodium rich minerals or the feldspars which form, and then you have got the potash feldspar. So this is how the different rocks form out of a magma because of the fractional crystallization, and as the temperature of the magma comes down, or as it cools, right here it has 1400 degrees centigrade temperature, and as it cools down, the minerals from olivine right up to the quartz are formed. Now this is a diagram that is just reverse of what we saw just now. Here we have got it shows that those minerals which formed at the earliest in the beginning, they are liable to be withered. They will get disintegrated earliest, and those which form at the end, like the quartz, they are the ones which will remain there as unweathered, or they will be the final product of the mineral composition, and ultimately quartz will be the one which will remain, which does not gets withered. So first of all, olivine here, and in this continuous series, the calcium rich feldspars will wither out, then pyroxenes, amphiboles, like this. So that means these minerals, they are the least stable under surface conditions, whereas the ones which form at the end, they are the most stable under the surface conditions. So the earlier a mineral crystallizes from the melt, the less stable it is at the surface conditions, and is more easily it gets withered down. Now here there are two figures. This shows, now here you can see that in this there is less of weathering, whereas in this you have got more of weathering. So whether a rock will wither out early or more depends on the type of rock and the length of exposure, how much time it has been exposed. So the question is, why should a rock disintegrate and decompose? In very simple words, weathering is response of the earth material to a changing environment. As I showed you earlier, those rocks which were formed at the deeper levels under very high temperature pressure conditions, those rocks, when they are exposed on the surface of earth, the surface conditions of the environment is different from what was the environment at the deeper level. For instance, after millions of years of uplift and erosion, the rocks overlying a large igneous body may be removed, exposing it at the surface. This mass of crystalline rock formed deep below the ground where temperature and pressures are high is now subjected to subjected to a very different and comparatively hostile surface environment. So for those rocks which formed at deeper level, the surface environment is not conducive, it is not fit for them, it is more hostile, so they would be very unstable there. I normally give a very common example. Suppose we have people living in our country, India, and some are living in the North Pole. Now, if they are asked to go to Africa, who are the persons who would be more comfortable in Africa? Certainly the ones who are living in India, because we are used to temperatures and the conditions which are not that worse, or say not that hot as in Africa, but almost of the same level. However, a person who is coming from the North Pole, he will not be able to withstand the conditions which are present in the African country. So similarly is the case with the rocks. So rocks, as a result of uplift, when arrive near the surface, encounter conditions very different from those under which they were originally formed, that is deep within the earth. Due to these conditions, minerals in the rocks react with the new environment to produce new minerals that are stable under the prevailing conditions. So due to this weathering, you have formation of new minerals which find themselves comfortable under the near surface conditions. Those minerals that crystallize at a high temperature from magma are most unstable, and the higher temperature of crystallization, the less stable they will be at the low temperatures. Low temperature conditions prevail near the Earth's surface. The rocks that are formed under intense temperature and pressure cool rapidly to form crystalline structures and minerals, and are less stable when exposed to low temperature and pressure at the Earth's surface. And hence, those rocks having the minerals which formed earlier are more susceptible to weathering. Then this weathering is classified into two basic categories, that is the mechanical weathering and the other is the chemical weathering. Mechanical weathering involves physical forces which break the rock into smaller fragments. So this results in the disintegration of larger rock into smaller and smaller pieces without changing the rock's mineral composition. Now during this mechanical weathering, there is no change in the rock's chemical composition. It is only the physically it is broken down into smaller and smaller pieces. Whereas in chemical weathering, the chemical constituents of the rock change into one or more new compounds. There are different types of mechanical weathering. First is the action of frost or ice. So the frost action, one type is known as the frost wedging. We all know what is a wedge. So you have cracks on the surface of earth. These cracks get filled up with the water precipitated, and in colder conditions this water freezes during the night time or during the colder conditions, and when this freezes, this forms, or it forms ice in the form of a wedge. And we all know that water has a unique property where it expands by almost 9% of its volume when the temperature goes below 4 degrees centigrade. And when this water expands by 9%, it exerts a tremendous pressure on the sides, and this wedge gradually it becomes deeper and deeper, and finally the rock is broken down into smaller pieces. As an example, if you fill up a glass bottle completely and put it in freezer, because of the expansion of water, the bottle breaks down into smaller and smaller pieces. So similar is the case with the rocks. When it is saturated with water and it is frozen, it expands and mechanically cracks and breaks open the rock. The second type of mechanical weathering is frost heaving. We know what is the meaning of heaving. Heaving means to raise up, to rise up. So if you put a lever below some heavy object and try to lift it, so that is heaving. So this, what happens, that the unconsolidated deposits that are present on the surface of earth, they absorb water, and under cold conditions this water, when it freezes, it expands and it heaves up the material which is lying above it. So the ice crystals which grow, they are also supplied water which is migrating from the unfrozen areas as thin liquefied films. Now in time, these lens-shaped masses of ice are built up and the soil above them is heaved upwards. It is dislodged from the ground and it comes out on the surface, comes up and becomes loose. So these are the type of mechanical weathering under the cold conditions. Similarly, under warmer and hot conditions, there is another process that is known as exfoliation. So exfoliation is a mechanical process in which large curved plates of rock are stripped from the larger rock mass by the action of physical forces. This produces two features that are fairly common in the landscape. So because of exfoliation, we have got large dome-shaped hills known as exfoliation domes, and that at a smaller scale, spheroidal weathered boulders that are present. Now when large masses of igneous rock, particularly granites, granite is a plutonic igneous rock which is formed at deeper level, when it is exposed by erosion and it fractures, or it has fractures and parting planes which are known as joints, they are found in this massive rocks once it comes out on the surface. These concentric slabs begin to break loose. It is just like peeling out of an onion. Onion, if you remove the outer layers, they come out. So similar is the case with the rocks, where the all along the joints concentric slabs begin to come out, and this the distance between joints is usually a few inches near the surface, but it increases to several feet as we move deeper. So on the surface, near the surface, the distance between the joints or the weak planes would be less, and as we go inside or deeper, the thickness or the width between those joints would be more. So the process that generates onion-like layers is called sheeting, and it takes place at least in part due to the great reduction in pressure that occurs at the overlying rock is eroded away, or because of the unloading of the overburdened material. So it has been observed that when overburdened material is unloaded, then there is a reaction, and because of that reaction you have development of weak planes or the joints. Here in this diagram, this is a batholith, which is large igneous plutonic mass. This has come up now because of the pushing from down below or the upliftment. The overburden material is subjected to expansion, and because of this expansion a number of weak planes or joint planes are developed as concentric rings on the surface, and this is uplifted. So you have got the sheeting where we can see that number of weak planes are developed and the rock material is removed along these sheets. Here is the diagram where we can see that very fine sheets of rocks have been formed on the surface, but if we move down, the thickness of this would increase. So this process of removal of the material in these sheets, this gives rise to the geomorphic feature which are known as exfoliation domes. Now at a smaller scale, these they produce spheroidal shaped boulders. Here I'll show you this diagram. This is a cross section of a boulder where the different, now this is made up of say it is a boulder of a granitic rock. Now the granitic rock, it has got a number of, it is constituted of a number of minerals. These minerals, when they are subjected to heating, they expand, and when they get cool they contract regularly for n number of years. Now because of this expansion and contraction, and these different minerals, they also expand and contract at a different rate. So because of this, the outer layer, by continuous expansion and contraction, it gets loose and the layers move out or they are peeled off. So this cross section through a spheroidally weathered boulder suggests that stresses set up within the rock. The stress is thought to develop as a result of the change in the volume. As now again, this granite, it has got a lot of feldspar mineral, which chemically when it is chemically weathered, it forms clay minerals which have more volume, and this also results in the removal of the layer. So the stresses, the both internal and external, lead to increased strain that eventually ruptures or peels out the layers from the outer side. Now if you look at this diagram, this is the original larger block of rock. It breaks, there are weak planes, and because of this it is divided into smaller pieces. Now you can see that at the edges it is exposed to the surface from all the sides, and thus there is more of weathering or decomposition of the rock on the corners, whereas here it is relatively lesser. So ultimately, in due course of time, the edges, they become rounded, and the rock, it attains the shape of a sphere. So here what I have tried to show you is that as the size of the rock keeps on decreasing, the surface area keeps on increasing, and chemical weathering, it acts on the surface of a rock. So as the rock breaks down due to mechanical weathering, more and more surface area is exposed and it is available for chemical weathering. Now here you can see this because of the weathering, you have got spheroidal boulders which have come out of this regolith. Regolith is the unconsolidated, loose and decayed rock debris on the surface of earth, and on the top of it you have the soil. So here you can see that the concentric rings, just like the peels of onion, they are removed and gradually the material gets withered out. So again, same, to show you the same thing, that concentric, very fine rings, they are layers, they are being peeled off, and ultimately in due course of time, in geological time, this entire rock mass, it is fragmented, broken down, decomposed into smaller and smaller pieces. Then we have the chemical weathering, the other type of weathering. This involves a complex process that alters the internal structure of a mineral by removing or adding elements. Now, as we discussed earlier, the minerals that crystallize deep underground from the water and oxygen deficient magma. Deep inside, the magma is deficient in water and oxygen. When it is eventually exposed to the surface conditions, where it can react with the abundant water, oxygen and carbon dioxide on the surface. So this helps in forming new and different different minerals. Now these minerals have got larger volume as compared to the original mineral. So when the volume increases, it helps in the disintegration of the rock. Now during this transformation, the original rock decomposes into substances that are more stable in the surface environment. The ones which I showed you, the olivine, pyroxenes and the amphiboles, which found deep inside the earth, when they are exposed on the surface of earth, they are not that stable, they are not in equilibrium with the surrounding conditions. Thus, the chemical weathering results in the formation of those minerals which are in equilibrium or in balance with the surrounding conditions. So consequently, the products of chemical weathering remain essentially unchanged as long as they remain in an environment similar to the one in which they are formed. So after chemical weathering, whatever the products are formed, they are formed at the surface conditions, and as such they remain on the surface unchanged. Now what we have on the surface of earth, we have plenty of water, oxygen, carbon dioxide. Now these are the things, or these are the compounds that are helping in the weathering. The water is very abundant on the surface. Although pure water is non-reactive, when a small amount of some other material is dissolved in it, it becomes active. Now oxygen, when dissolved in water, it oxidizes, just like the rusting of a nail. Similarly, carbon dioxide, it gets easily dissolved in water to form a weak carbonic acid. Now originally, the original pure water was non-reactive, but the one having dissolved carbon dioxide, it is acidic in nature, and this mixes with the rain, and the rain dissolves some of this carbon dioxide, and then this water when it is the rocks are exposed to this water, they start reacting. The carbonic acid, it forms very reactive hydrogen ion and the bicarbonate ion that we'll be seeing just now. Now there are different types of chemical withering. The one which we were discussing about the formation of carbonic acid. So first type of chemical withering is carbonation. So it is the chemical reaction of carbon dioxide to give carbonates, bicarbonates and carbonic acid. Like water, it mixes with carbon dioxide, it produces carbonic acid. Similarly, calcium carbonate, which is there, the calcium carbonate, you have got the calcite and the limestones on the surface of earth. When they react with this carbonic acid, they form calcium hydrogen carbonate. To illustrate how the rock chemically weathers when attacked by carbonic acid, we'll consider the weathering of granite, which is the most abundant rock on the Earth's surface in the continental part. And granite, it is constituted mainly of quartz and potassium feldspar. The weathering of potassium feldspar present in the granite takes place by this process where potassium feldspar, which is potassium aluminum silicate, it combines with carbonic acid and water and it forms another mineral where the OH is attached to the aluminum, and this forms the clay minerals along with ions of potassium bicarbonate and silica, and these become in solution and they get washed away with the rainwater. So the resultant formation is the formation of clay minerals. Now the clay minerals, they are very stable on the surface at the surface conditions as compared to the feldspar which is present in the rock. Now so here you can see that you have got water and carbon dioxide, it mixes to form the carbonic acid. This carbonic acid, it disintegrates into very reactive H ion and the HCO3 ion. Now when these hydrogen ions, they react with the feldspars, then the H, the hydrogen, it replaces the potassium part of it and forms the clay minerals, and this silica, bicarbonate and the potassium ion, they are released in solution. They go out in solution. Similarly, when the carbonic acid, it comes in contact with calcium carbonate or the limestones or the calcite, then again here this sorry, H ion, it combines with the CO3 and forms the bicarbonate and calcium, which is removed as now the other type of chemical withering is through the process of hydrolysis. Hydrolysis, as we know, is a chemical process in which the entire molecule of water is added to a substance, and this causes both the substance and the water molecule to split into two parts. In such reactions, one fragment of the parent molecule gains a hydrogen ion. Now here we have this olivine, which is magnesium silicate, here the hydrogen ion, it combines with the part of magnesium silicate, that is the silicate. So this forms the hydrogen silicate, that is silicic acid, and then the other two magnesium and OH ions, they come in solution. So you have the breaking off the olivine molecule, and then these ions, they come in solution. Similarly, the olivine, when it reacts with carbon dioxide and water, then again you have the formation of silicic acid, bicarbonates, and the magnesium ions, which come in solution. So the olivine, it breaks down, or it weathers down due to the addition of water molecule. Then next we see the case of orthoclase. It combines with carbonic acid and water. So here again the water, it breaks down, and the OH part of the water, it combines with the aluminum silicate part of the orthoclase, removing away the potassium ions, and it forms another clay mineral that is known as kaolinite. And the others, the silicic acid and the potassium and the bicarbonate, they come in solution. The only common rock forming mineral that is not affected is quartz. Now, as I showed you in the beginning, in the where I showed the Bowen's reaction series, the quartz was the end member. It had formed in the last. So the quartz, it does not react with either the carbonic acid or water, and it becomes chemically resistant mineral, and that is why quartz and clay, which is formed by the chemical weathering of the feldspars, and the quartz, which is silica, which is produced out of the disintegration, they are the most common minerals present in the sedimentary rocks. So they disintegrate and form sediments, and hence they are the most common part. Next process of chemical weathering is hydration. Hydration, as we know, is the attachment of a water molecule or absorption of water. In this, the chemical bonds of minerals are changed as they interact with water. The combination of mineral or the element with water increases the size of the chemical structure. Now, when water is added, the overall size of the structure is increased, thereby becoming unwieldy and thereby loosening and the disintegration. So, as an example, we have the hematite. The water molecule is attached to hematite to form another mineral, which is known as limonite, which is here you can see that the water is attached to the molecule of iron oxide. Similarly, anhydride, which is calcium CaSO4, the water molecule is attached to it, and a new mineral, that is gypsum, which is commonly found in the sediments, this gypsum is formed. So that means the anhydride, it swells up, it attaches or absorbs the water molecule and forms another mineral, that is gypsum. Then oxidation, we all know, is the combination of oxygen molecule, and the most common example that we are familiar with is the formation of the iron oxides. Now, a number of rocks, they contain iron, so when they are exposed to the surface conditions, the oxygen combines with the iron to form iron oxides, and this gives reddish color to the withered rock, as well as another, the soil formation of laterite soil, which you must have heard of, is because of the process of oxidation. These are the simple reactions that are taking place with different minerals that we have discussed earlier. So these are the chemical equations. Then another type of withering is the biological withering. The plants and the animals too contribute in the withering of the rocks. The rocks, when they are exposed on the surface, they have a number of weak planes present in them. Now these weak planes are the sites where number of plants and burrowing animals, as well as the humans, they interact with the surface condition, and they grow or within these cracks. Now the plant which germinates on the rock, the roots, they enter into the weak planes or the joints, and as the life process goes on, the plant keeps on growing. The roots which go inside the cracks, they also undergo the normal life cycle, where the water and carbon dioxide is available in the roots. Now these water and carbon dioxide, they react with the surrounding minerals like the feldspars if they are present, and the feldspars, then as we discussed earlier, the feldspars, they react with the carbonic acid and the hydrogen, and the hydrogen released from the combination of water and carbon dioxide, and this results in the growth of the roots. Now the clay minerals which are formed as a due to the combination of the feldspars and the water and carbon dioxide, they release potassium ions, and these potassium, they provide nutrient, or they act as provide fertilizer or nutrients to the plants and help them to grow. Now as the root keeps on growing, it exerts a mechanical force on the rocks, as can be seen here, that this plant root has entered and it is exerting a lot of pressure, and hence this rock will in due course of time break away. The same thing is we have observed that we don't allow the plants to grow on the walls of our house, because the plants, the roots will mechanically enter into the cracks and crevices, and ultimately they dislodge the bricks and loose open the walls. So the normal practice is to remove those plants. Similarly, there are burrowing animals that break down the rock by moving fresh material to the surface, and then the chemical and physical processes that are taking place in the burrowing animal, due to their living in those cracks, then they provide certain chemicals which again help the rock to chemically wither. The decaying of the organism produce acids that contribute to chemical withering. So the plants and animals contribute directly or indirectly to chemical withering, since their life process produces oxygen, carbon dioxide, and certain acids that enter into the chemical reactions with the earth materials. Now we have seen the different types of withering. Now the withering rate, at what rate will the withering process proceed? it depends on a number of parameters like the type of the rock or the mineral composition of the rock, then the time for which it is exposed, the slope or the topography, how the surface is like, then the structural discontinuities, the structural planes that are present, and most important, the climatic conditions prevailing in the region where the rocks are exposed. Now, rocks are basically like we saw, the ones which formed earlier, the olivines and the pyroxenes. They are also known as the made up of mafic silicates. Now, the deeper rocks, the mafic minerals or the rocks are the ones which are darker in color and they have got higher specific gravity. Now, these minerals, as they form in the deeper part, they tend to weather much faster as compared to the other type of minerals referred to as felsic minerals, that includes quartz and feldspar. Felsic minerals are the light colored minerals having a specific gravity of less than 3, so they are relatively lighter. Now, the minerals that form at earliest deep inside the earth tend to disintegrate in the beginning. This we have discussed a few times. Then the different minerals show different degrees of solubility in water, like you have calcium carbonate which readily dissolves in water as compared to the others. So calcite, being soluble in water, is more prone to weathering even as compared to the feldspars. Feldspars otherwise, they, with the action of water and carbon dioxide, they weather out or form the clay minerals, but calcite, which is calcium carbonate, it is more soluble as compared to the feldspar. So rocks that are resistant are composed of minerals that are relatively unaffected by chemical weathering. So the rocks, like you have got the sandstones. Sandstones are the rocks which are made up of the silica or the quartz, mineral quartz, and quartz, as we have discussed, is the one which is least prone to weathering. So sandstone will be more resistant to weathering as compared to limestone, which is made up of calcium carbonate. So quartz is a classic example which is unaffected by dissolution, hydrolysis and oxidation. Therefore, rocks composed almost exclusively of quartz are more resistant than any other rock type. Chemical weathering occurs fastest at the sharp edges of the rocks as they have large surface area. This we had shown in the diagram, where the corners, they are more susceptible to weathering because they get exposed from all the sides, and therefore the corners are removed easily. So ultimately the edges, they turn into rounded surfaces. Now, one important thing which we have discussed, that chemical weathering, it takes place on the surface, and because of mechanical weathering, the surface area keeps on increasing. So as the mechanical weathering progresses, the surface area keeps on increasing, and this helps the chemical weathering to take place. Therefore, mechanical weathering, it adds to the effectiveness of chemical weathering. Now the next was topography. The topography of the area decides the time of contact of rainwater with the rock surface. Now suppose the area has a higher slope, the water will drain off easily. However, if the water is able to stay on the surface of rock, it has got time to react with carbon dioxide for carbonic acid and then carry out other reactions that we have discussed. So In case the area has a flatter topography, then the rocks are more prone to weather out as compared to those areas where the slopes are steeper. Now, climate is a very important parameter that has a key role in the chemical weathering and chemical reactions that are taking place. In warm and humid climates, there are more weathered rocks, and subsequently the rates of weathering are much higher in comparison to the cold and dry climates, because chemical reactions progress faster in the presence of high amount of water and higher temperature. So higher the moisture content, higher the temperature, more is the chemical weathering. It facilitates the reactions to take place. That is why the rocks in the tropical regions, that is the ones which are exposed to abundant rainfall and high temperature, weather out much faster as compared to those present in the cold and dry regions. Then next is the time of exposure, or the length of exposure. So the longer the rock is exposed to the agents of weathering, the greater would be the alteration and the amount of weathering. Then we have been discussing that the rocks, it has a number of structural discontinuities or the weak planes in the form of joints, fractures, fissures, and even the bedding planes. These weak planes, they provide potential surface for both physical and chemical weathering to act. Such features also provide easy pathways for the entry of the reactants like the water, carbonic acids, even the providing space for the roots and the burrowing animals that facilitate the chemical as well as the mechanical weathering. Thus, the more massive rock is slower, the more the massive rock is, the slower would be the weathering, or vice versa. If it is not massive, it has a number of discontinuities, the rate of weathering would be faster, whereas if it is a massive rock, the rate of weathering would be lower. So that is why weathering in the granites, which are massive in nature, it occurs slower as compared to the sedimentary rocks which are layered, which have a number of discontinuities. So there is a term known as weathering index. This term is used in order to measure the intensity of chemical weathering. In this, there is a comparison made between the mineral or a chemical compound that is relatively stable with the one that is rapidly removed by the weathering. For example, quartz is very stable as compared to feldspar. So the ratio of quartz and feldspar is taken as a weathering index. Similarly, the resistance heavy minerals like zircon and tourmaline, a ratio is made between them and the amphiboles and the pyroxenes, which are less resistant. So these are some of the parameters to quantify the amount of weathering that is going to take place. So this term is known as weathering index, and you will be using this term in due course of time. Now, what are the products made out of weathering? Well, the weathering, as I told you in the beginning, has been responsible for giving us the external or the exterior of the earth to quite a large extent. Here, this is a very good example of a balancing rock in Jabalpur area. Now the thing is how this piece of boulder, how it is resting over this mass, rock mass. Now this is a granitic terrain. Now because of the mechanical and chemical weathering, somehow this boulder has remained there because the center of gravity of it is passing through this point and it is still balancing. So it's a spectacular spherical shaped outcrop which is present in the area, and it is produced out of weathering. Similarly, we have such beautiful landforms which are present, like this is because of the differential weathering. Differential weathering means the rock, it is made up of several layers. Now each of these layers is not prone to the same amount of weathering because of the different chemical composition and the structures present. So they weather out differentially. Some parts will weather more like this and the others will weather relatively lesser, and this results in giving rise to this picturesque or spectacular landforms. Similarly, there is a Maltese cross formation in South Africa where this rock mass has weathered, the lower portion has weathered more as compared to this, giving rise to features similar to Maltese cross, and this is another feature which we see, the landform which we see produced out of weathering. Then weathering is also responsible for giving us some new minerals and rocks, like the bauxite, which is common aluminum ore. It is produced chiefly by the weathering of aluminous rocks. Then the lateritic soil, which we have read a number of times, it is a soil which is rich in iron and aluminum, and it forms in the hot and wet tropical areas. So this lateritic soil, it is also produced out of the weathering, and the oxidation takes place. You have the formation of iron oxide. Then we had discussed about the regolith. Regolith is the blanket of the unconsolidated, loose and decayed rock debris having varied thickness. Now the regolith, it is a withered or decomposed rock which from a distance it appears as the bedrock. However, it is highly decomposed. Upon touching, it will break open or it will become very loose. Now on the top of this regolith, you have the formation of the soil. The soil formation or the pedogenesis involves a number of steps. So it is the organic activity, it takes place. So this gives rise to the formation of soil. So formation of regolith and soil. Soil again, it is produced out of the weathering. So here at the base you have got the unweathered parent rock material. Then this soil horizon, it is divided into such horizons O, A, E, B, C horizons, where O is the organic or the one containing organic material or the humus material. It may be very thin or thick depending on the amount of the organic material present. Then below this you have the topsoil, the horizon E. Then below it is the least clay minerals and organic material which forms the E horizon. Then the B horizon, which is rich in minerals that least moved down from A or the E horizon. Then the C horizon is the one which is the parent material, or we can say it is the regolith material, where it has just disintegrated from the rock, and below this you have the bedrock. Now the thickness of these horizons depend on how much time has taken place for the formation, or how much time the area has been exposed to the process of weathering. Now here is an example that where the man-made activities have been causing the chemical weathering. We know that a lot of H2SO4 is released by the petroleum industry around Agra, and this sulfur dioxide which goes up in the atmosphere, it combines with the atmospheric water vapor, water, and then you have the formation of the sulfur dioxide, H2SO4, H2SO4, and this H2SO4 it is reacting with the pure calcium carbonate, of which this Taj Mahal is made up of. So it is a chemical weathering taking place because of the man-made activities. Thank you.